This week we'll be looking at the behavior of capacitors in circuits. The mathematically simplest case is the parallel arrangement of two or more capacitors. We'll just look at the simple case here with two capacitors first and generalize it later. Two capacitors in parallel are connected by a wire at their top plate and a separate wire at the bottom plate. That implies the voltage difference across the plates must be the same. Using our relationship that Q, the charge on each plate, the magnitude of the charge on each plate, is equal to capacitance times the voltage difference between the plates, Q equals CV, you can state that V1 and V2 are equal. They will both be equal to the voltage of a battery or a power supply attached as shown. In the microscopic picture, we should think of both capacitors as starting out neutral, and then electrons feel the presence of this higher voltage at the positive terminal of the battery. So these free electrons in the top plates are going to travel along the wires towards the battery. And the battery will push, using its electrochemical potential, push electrons out the negative side of the battery. And those electrons have nowhere to go but to be deposited on the lower plates of these two. So the question is, how would these two capacitors in parallel behave if we treated them as a single capacitor, meaning pull them out of the circuit and put in a single equivalent capacitor that would have the same system properties? The equivalent circuit here gives you the relationship we need. V equals Q on each plate divided by the capacitance, CEQ. We must demand that all of the charge that leaves these two plates together is going to leave the top plate of the equivalent capacitor. Right? They have to behave in the same way, so we have the equivalent capacitor charge will equal the sum of the two charges that left capacitor 1 and capacitor 2. So you might think of this as saying that the charge splits up between these two capacitors, or the charge is additive to give you the total. Replacing Q with CV in this expression and the fact that they all carry the same voltage gives you that the equivalent capacitance is simply the sum of C1 and C2. This is valid for any number of capacitors in parallel. So you can add up arithmetically the capacitance of each, and that will give you the equivalent capacitance of this device. Now, instead of thinking of these capacitors in parallel, let's take a look at the series case. In class, we define what being in parallel and being in series means. In series, the head or positive plate of one capacitor will be connected to the tail or negative plate of the next. And once again, I will just address the case with two capacitors, and then we'll generalize to any number later. So remember that these electrons want to reduce their potential energy. They will do that by climbing up the voltage hill. They go to the high voltage, which reduces their potential energy because they're negatively charged. The battery pushes them through with electrochemical potential, and the electrons are forced back uphill to a place where they don't want to go initially. The electrons travel to the negative plate. They don't want to hang out together, so eventually they will build up enough electrostatic repulsion to keep more electrons from coming over to this plate. You can see that now free electrons that are in the top plate of capacitor 2 will naturally want to travel away from the electrons that were deposited down here. They feel a push, so they go the only place they can go by this connection, this wire. They go up to the negative plate of capacitor 1. So you see that whatever charge leaves the positive plate of C2 is constrained to stop at the negative plate of C1 because everything began neutral in the circuit. The sum of these negative charges and these positive charges must remain zero during this capacitor charging process. All capacitors in series, therefore, must obtain the same charge Q. So instead of the case with capacitors in parallel, which all had the same voltage, now capacitors in series must all have the same charge. Applying our Q equals CV relationship once again, and the fact that all Q's must be the same, equating that to the Q that would build up on our equivalent capacitor, we'll just set that equal to Q. In this situation, the voltage drop across capacitor 1 and capacitor 2 must add up to the voltage drop across the battery. Right? They're connected by wires. This voltage drop must equal that voltage drop. So when you make this statement, the battery voltage V is equal to V1 plus V2, we have Q over C in the equivalent circuit must equal Q over C1 plus Q over C2. All the Q's are common, and we have an inverse relationship now, that the inverse of the equivalent capacitance is equal to the sum of the inverses of the individual capacitors. I've only done the case for 2, but this is valid for, again, any number, capital N, of capacitors that are placed in series with one another. You take the inverse of each capacitance, sum those inverses, and then invert that entire sum to obtain the equivalent capacitance. And you'll see after you do a few of these problems that the equivalent capacitance must necessarily be smaller than the smallest of all of the capacitors in that series arrangement.